Kayenta is designed to be a standalone system. It doesn't have to work with Spinnaker. And it of course uses the libraries of Spinnaker to have this extensibility, scale. It uses Redis and Orca. It uses the storage systems like S3 if you have configured GCS for storing the intermediate data that it extracts from the storage. It has quite a few integrations with data stores. It had Prometheus, Stackdriver, and Datadog. Now I think InfluxDB is also in there. SignalFX is coming soon. It's very nicely integrated UI with Spinnaker. You can actually see the configurations. You can run it in a retrospective mode as well as the real time. So it's pretty cool stuff. So yesterday, some of you may have attended the metrics talk given by Michael Graff. This is a simple flow for the Kayenta. One is to fetch the metrics. So you probably have seen in the UI in Kayenta's setup in the Spinnaker, you have to give it a scope and specify what is your baseline, which is the real thing, and then the canary, which is the experiment. And once the Kayenta this starts, API is called, it goes and fetches the data, it cleans the data, aligns all the data together, and passes it to the judge, which does a little bit more cleaning with respect to nans and things like that. Does the metric comparison using classifiers, and then computes the score. So there are 3 stages there. One is the data cleaning, one is the comparison. These are the classifiers. And the judge itself can use one or more classifiers depending on how you want to use that. Right? So this is a little bit more detailed than the previous one. Once the canary starts, the judge, the Kayenta system breaks it down into multiple tasks. It's a data fetching part. It does a lot of retries. There are some additional reliability things that are built into that for the collection of the data. And then the metrics can be grouped for scoring. There are weights that you can give to the groups. And those are all done at that point, and then send it to the judge. Judge interface itself is very simple. It takes the metric pairs, essentially the baseline and the canary pairs of the data, which are aligned with the timestamps, and it expects a result back with the configuration that's passed in. The configuration is per metric configuration. Maybe you can quickly look at how the configuration looks. So you can go select metrics from your data source. And for each one of the metrics, you can specify what group that falls into. You can specify the direction it needs to fail on. Is it increase or decrease or either? And the criticality refers to the system where if a particular metric that we think is critical fails, you fail the entire canary, right? And the NAN strategies and the filter templates. Scope essentially refers to, in Kubernetes kind of a thing, maybe it's the namespace or the server group that's being installed, replica set that's being deployed. It depends on a little bit on the metric store that you're using, how you specify these scopes. And you can also provide label bindings. In some of these metric stores, if you group by, if you have multiple metrics that are coming in, which all have slightly different tags. For example, CPU utilization can have a system versus user versus idle. You can get all of them as separate groups and compare them separately, right? The judge interface, like I said, is fairly straightforward. It takes the canary config, which is what we saw in the UI for individual metrics. So it only takes score thresholds is what it refers to as pass or fail classification. So when it scores for a group, you can say whether it's a pass or fail based on the threshold, the minimum threshold, and the maximum threshold that is set for the judge. For example, you can say 70 or below is a fail, 90 or above is a pass, somewhere it's in the gray area, right? But individual metrics themselves have a 0 or 100. right? Pass or fail. That's a classifier, the way the algorithm that's being used. And once we call the judge, the class groups that needs to be implemented are essentially the judge class. Judge basically is an overall class that calls the classifier for individual metric. Classifier is a way of saying pass or fail for individual metric. You can think of classifier as, let's say you're taking an average for the metric. The classifier would then look at average of baseline, average of canary, and then says if they are same, it's a pass. If they're not, it's a fail. That's a pretty strict comparison, which usually always fails. But as an example, that would be the classifier, right? So it calls first it calls the data processors. Some of this data that's coming in, for example, errors in some of these collection mechanisms, if there are no errors, there is no data for the timelines. It only sends the data when there is an error. It's also incremental sometimes, right? So those things we need to take care of. And if the data is coming in that has not a number in them, so you have to decide whether you want to replace that with a 0 or ignore that data, replicate the same data. Those kind of things can be done with the data processors. Classifiers, as we discussed, is where you can have an average classifier or some other classifier. Right now, the default implementation is something called a Mann-Whitney Wilcoxon-Cox classifier. What this one does is it's a non-parametric classifier. If you're familiar with the statistical terms, the parametric classifiers usually are parameters that you use to compare one another. That would be something like your mean, standard deviation, right? Variance, those kind of parameters. You would say, I have the distribution for the baseline that is coming in. I have the distribution for the canary. How do you compare these two distributions? There are multiple ways of doing it. The simple ones would be something like a t-test, which is a pretty common, which assumes certain things about the distribution, like the normal distribution. And then you can say, is my mean the same? Is the standard deviation different? Based on that, you'll say it's a pass or fail. Right? You can say if my standard deviation is 10% within the range, and the mean is 10% within the range, pass it. But Mann-Whitney classifier is an interesting one here. It does not use these parameters. It just picks an element from the baseline from the canary and says, is it above or below the median that I expect from the baseline? And it does that statistically for all the parameters. And if it comes out to be almost the same, half of them are above, half of them are below, it says, yeah, it's a pass. They look very close, right? So that's the default classifier that's implemented. So we can quickly look at the default judge implementation. So this is the Kayenta project. This is IntelliJ. This is not my development machine. So that's the Kayenta project. As you can see, the way it's organized, each one of Kayenta core is the base one that has Orca, Redis interactions. And you can see this Atlas, Datadog, GCS, InfluxDB. These are all the data stores in some form or the other. For this particular talk, we are mostly interested in the Kayenta Judge. Right? In the Kayenta Judge, if you see, it's also organized as classifiers. This is what we just spoke about. And scorers is where it takes the classification output for individual metrics. Say you have one CPU metric, one memory metric, and one latency networking kind of metric. It takes those metrics. Each of these groups currently have weights. So the scorer is the one that applies those weights to individual groups and then computes them. There are a lot of changes that are coming, but that's the current implementation. Right? And the detectors is another thing where it removes the anomalies in the data. Anomalies are defined as something that you don't expect to see, a very short burst or something like that. So for us to compare the baseline and canary, we want to make sure we are comparing their normal behavior versus trying to do something anomalous behavior. So if there is a small spike, then you would remove that small spike. There are multiple techniques. I think we have these implementations as IQR implementation, sigma detectors, right? This simply is saying if I'll compute 95 percentile, anything above I will remove. Usually you don't want to remove more than 5% of the data to make sure the distribution remains the same. That is being done. And the judge is the one that's an implementation. Here you can see the judge has this canary config as input, thresholds that are being sent to return as a pass or a fail with the data. Right? These are the ones that you would overwrite. And the matrix pair list. Sorry. So matrix pair list, score thresholds, and canary config. Output is the canary judge result. The canary judge result would include pass, fail for each one of the metric pairs, overall score, and the group score. Because we have some metrics that we can group, it also computes the group score for them. Right. Then, so what we'll do today is take a simple example to add to the Mann-Whitney classifier. We will add a threshold-based classifier. It's basically saying, okay, if you have two distributions, it may not have the same distribution when we compare with Mann-Whitney, but they're close enough, developers don't really care. Right? They're 10% off from each other or 5% off. Maybe because of the way the metric is chosen, they start off at different levels, but they continue. And it fails, but really developer doesn't care for them to be failed. And the other one that we will do is we can, if we say we can compute weights for these metrics externally. So we have sometimes when you select a particularly Netflix kind of scenario, they have extensive metric collection mechanism. They have gateways. They collect data for each of these APIs. If a service has 10 different APIs, it collects 10 metrics per API, you got 100 metrics just at the API level. And so in those situations, the developers are not really fully aware what's important, what's not, based on traffic patterns. There are ways you can compute which are important, which are not, based on the long-term data. So let's say we compute those weights externally, then we can assign it to them. So the one example here is here, this is the CPU time, I think. So they started off at slightly different. They continued. They're almost the same. But you can see that they are at different levels. Right? If you're doing a non-parametric comparison, clearly they're not the same. One is always above the other. So this kind of thing will fail. But if you take a parametric comparison and say, hey, where is my mean? Is it within the range of some 5%? Then yes, they are within the range, and you can pass them. This is a real example. There are other ways of dealing with this, but for this purpose of the demo, we're going to do implementation for this. So here, what we will do is we'll create a percentage classifier, essentially copy-paste the existing kind of classifier with its interface, add code to compare based on the distribution metrics, and then return pass or fail to it. What we'll also do is, in statistical world, people use something called ensemble approach. When you don't know what is right, you do 4 things, and then say, we'll leave it to God and see which one works, kind of thing. So this ensemble approach, actually, in this particular case, combining Mann-Whitney and threshold actually gives slightly better results. We'll just say how to combine those 2 classifiers within the judge and get a better result. Right? When you do a compare, it checks what is the % change from the control, which is the baseline, to experiment, which is the canary that is deployed. Here we are also making some assumptions on when you're comparing these metrics, there are some control parameters that we assume to be the same. That is, the input load that they are processing is equivalent to each other. That's exactly the reason why we deploy both the baseline and canary at the same time to compare. We also are negating a lot of the long-term effects. If a system has been running for a long time, there probably were high loads at some point. That would have increased its memory cache usage, but at this point, they may not be high, but still the cache would look high. Right? Those are all assumed to be controlled. And here, we just do check is pass. We basically use the upper threshold and lower thresholds. So you can also have this little bit more sophisticated, maybe Netflix internally has the implementation. You can say, if it is latency kind of a metric, if it is higher by 10%, you should fail, but if it is lower by 20%, you should still pass. Right? You can have things like that set up depending on the metric. So CPU utilization would be similar. If it's a higher CPU utilization, you may want to fail, but if it is a lower, it's okay, but it should not be too low. If it is too low, then there's something else wrong. Right? So all it does is looks at it within the thresholds. If it's high, low, and then if it will pass if it is all within the range. Right? So that's pretty much I wanted to show. In terms of learnings, you have to be careful about what kind of metrics you want to choose, how many metrics you want to choose to get less false positives or false negatives. For example, the metrics that some of them I have chosen, the CPU metrics, they're collected by Prometheus. These metrics are cumulative metrics. In some cases, for errors and cumulative metrics like this, it may, not errors, but for these kind of metrics, it may be better for using rate of change as a metric for comparison rather than the metric itself, right? So then you know how much exactly at individual time period the data is changing to compare them better. In some cases, you may want to use percentile data collection. Say if you're comparing latencies, you really don't care some changes. Your SLA is 300, your system is at 100 milliseconds. Now, if you could say, hey, my 90 percentile data, if it is different by more than 20%, then I want to be failing it. Even with the current default implementation, you take the 90 percentile data and compare. That may give you a better visibility into your system performance. Right? And how the developers use these metrics is slightly different than how the operations people like to see these metrics, what we have seen. So for this canary, it works best with the operations kind of metrics rather than the developers where they take 400 metrics or 1,000 metrics and try to see all of them. At Netflix, they have huge amount of traffic. For them, 1% of the traffic is like more than anybody others can handle. So for smaller people, running this canary analysis with that small amount of data may also not give right results. So you have to make sure the traffic that you're seeing is representative of your canary. You have to compute some confidence scores based on them to make sure your canary is actually giving you the result that you expected for the time period. Right? And the other thing we have seen is for most of the services, the metrics collection is not very good. If you have the gateways in front, which are collecting all the latencies, throughputs, for example, Istio does, Netflix has their own gateway API, which provides all that data, it gives much better results. So you should consider having some kind of application performance monitoring metrics or gateways which can give you that core insight for the KPIs for all the interfaces. Having combined data for all interfaces together is one thing, but knowing how individual interface is working gives you better diagnostic information, ability to fix them quickly. Right? Yeah, in conclusion, the Kayenta is awesome. Most people who use it really love it. But there are some improvements that you can do. Primarily, I think there is some context information that can be passed that can extend the computation or analysis much better and less burden on the developers. Right?